Hello, Kainatis. This is Kainati Chai, and we will be having a conversation in English, but you will be able to find subtitles below in Urdu, Hindi, in English as well later on. But let me introduce our guest. We have Dr. Parvathy Prem. She's a planetary scientist at the Johns Hopkins Applied Science Laboratory, so APL, or with the Desi style, it's laboratory. I should also say that. She was born in Kerala, India. She grew up mostly in Kerala, and some of her time was in England as well. Her major was in aerospace engineering from Nanyang Technological University. So that's NTU in Singapore. And then she came to the US for her PhD at University of Texas at Austin. And then she went for her postdoc, where she is right now at Johns Hopkins University in Maryland. We'll be talking about her work as well. A lot of her work is about the moon and about understanding it, but through computers and computer simulations and things like that. So we will see how do we learn about that. So first of all, Dr. Prem, welcome to Kainati Chai.
Yeah, thank you, Salman, and I guess hello, Kainatis from me as well. I should say Salman didn't promise me that there would be chai, so I mean he did tell me there wouldn't be chai, so no false pretenses there. And just as a very minor correction, so you said applied science lab, so
Physics.
it's the applied physics lab. So APL, in case anyone was listening very carefully and spotted that.
My apologies. Yes, I was reading physics actually, but it was translating into applied science. I think that's one
I
of
know
those things. But thank you. No,
it's all the
APL.
same.
APL. So thank you very much. So, I mean, you have been in different places. You are coming from computational side, but doing astronomy. I'm just curious, what prompted you to get into astronomy? How did you get interested in the sciences?
Yeah. So I was never one of those kids who was, who always knew I was going to be a scientist. I didn't. I think the one maybe constant thread in my life is that I've always liked stories. I've always liked listening to stories and telling them. And so for me, a large part of science is storytelling. But in terms of how I got into the work that I do now, so growing up in India, in the in the 2000s, it was still a case of, well, do you want to be a doctor or do you want to be an engineer? If you were at least at all scientifically inclined, those were kind of the only two professions that anyone was aware of. And so for me, my parents are both doctors, so I knew I didn't want to be a doctor. They love their jobs, but there's very little work life balance. So I knew I didn't want to be a doctor. So I figured I would study some kind of engineering, and I knew I liked physics, I liked maths, and I'd enjoyed whatever fluid dynamics we had done in high school physics. And so I applied to the aerospace engineering program at NTU, where I did my undergraduate degree. I wasn't really thinking much about what I would do afterwards. I assumed that something would come along. But towards the end of my undergraduate degree, I didn't have a lot of research experience during my undergraduate studies, but what little I had seen appealed to me, and so I had this idea that I would like to learn more, and I would like to give this research thing a try. I was also, profession wise, I was interested in becoming a professor at a university at some point, and so I knew that to be a professor you had to get a PhD. So towards the end of my undergraduate studies, I applied to several PhD programs. So I applied to, and when I was applying to PhD programs, I was really looking. So I knew I wanted to do computational work of some kind. Like I in addition to physics and maths, I also knew that I liked computer programming, and so I was looking for something computational. I was mostly looking at aerospace engineering departments, and there was all kinds of interesting research going on. So I was thinking, maybe I would work in wind energy, help to design wind turbine blades. There were a few labs that were doing what I still think is very interesting work, studying how birds and insects fly and what we can learn about building better aircraft by looking at dragonfly wings and birds and bats and even jellyfish. And then where I ended up was at the University of Texas, where my advisors, David Goldstein and Philip Varghese, had a group of students who were in the aerospace engineering department, but they were using computational techniques that had been developed for engineering problems. And they were taking those and applying them to planetary science problems. And so UT Austin was one of the places I applied, and it was one of the places where I was accepted. And my advisors, I came along at the time when they had just received some funding from NASA to hire a grad student to try and study how the moon got its water. So I started my PhD in 2010, which was just a year after a NASA mission called LCROSS had found the first really definitive proof that there was water ice near the south pole of the moon. And so timing wise, one of the big science questions at the time was, where did this water come from? And I came along at a time where I was able to spend my PhD building computer models to look at that question. And as I got deeper into it, as I started reading more about planetary science and going to conferences, meeting other planetary scientists, I realized that, this was a profession that I would really like to be in. I mean, it brought together a lot of the things I like. I mean, that there was still the physics and maths and computer programming, and there's also you add in a bit of imagination and a bit of storytelling, and so I decided I wanted to be a planetary scientist. And then when I was finishing my PhD, I applied to several different jobs. The only one I got was the one which ended up becoming my current job, which was the postdoc position at APL. So I was a postdoctoral researcher for 3 years, and then I stayed on at APL as full-time staff.
Well, that's such a fantastic story, and I should mention that this question, oftentimes people ask, how do we, especially from South Asia, and in particular from Pakistan, when you don't have that many opportunities, for example, to become an astronomer, right? And so people ask, okay, so what other fields can you do? And so I mentioned like astrobiology. You can do biology, mix in with astronomy, or you can do, astrochemistry, or you can do sort of like various types of things. You can do geology for planetary stuff, and one of the ones which is computational. I mean, there is a lot of stuff regarding cosmological simulation. So again, and in my mind also, when I think about computational astronomy, I think about simulating the universe, for example, and things like that. And your example is a great one of that. It's not just about the universe, but actually thinking about like the moon, for example. And I know you are also interested in Venus, Mercury, and asteroids too. We're going to come back to it in a second. And one other thing I should say, and it was interesting that you mentioned your interest in flying insects and stuff like that, because the Dragonfly mission that is going to there are plans for a Titan mission.
Yeah.
That's using the similar kind of principle. By any chance, are you going to be involved with Titan, or is it just more local moons? I'm just curious.
Yeah, that's a great question. So one of the most exciting missions that APL is working on right now is the Dragonfly mission, which is it's a helicopter with 4 sets of blades, and it's going to Saturn's moon Titan sometime over the next few decades. So I'm not personally involved with that mission at the moment. So a lot of my work tends to focus on solar system worlds that have very thin atmospheres. And one of the things that makes Titan special, and the reason why NASA is sending a flying spacecraft there, is because the atmosphere of Titan is actually a little bit thicker even than the atmosphere of Earth. So one of the things that the principal investigator of that mission, Zibby Turtle, often says is that, you know, on Titan, if you could almost fly by flapping your arms. And so Dragonfly is not something I'm directly involved in, but I have a lot of colleagues who are involved in it. So I'm very much looking forward to
That's
its
that's
journey.
uh, that's really cool. Okay, so let's talk about the moon. And first, just from the science perspective, because I think that was a big discovery, and that was by, I think, Chandrayaan 1 as well, which was an Indian mission orbiter around the moon, and then of course you mentioned El Cross. So there is now evidence for water, like, you know, that
Mm-hmm.
okay, well, there is water ice on the moon, and that's where a lot of the interest of a lot of the missions that are going, because that, I mean, in some ways that has been a game changer in terms of we don't have to bring water to the moon, you can use water there. Tell us a little bit about what your research is, and which is about the origins of water on the moon, and how do you go about, I mean, how do you use computers to figure out where the water on the moon came from?
Mm-hmm. Yeah, good question. I ask myself that every day. So taking a step back. So for a long time, people used to think that the moon was mostly dry. Um, well, actually, if you go even further back, at one time, when people looked through the earliest telescopes or just looked up at the moon, we used to think the moon had oceans.
Right.
And, you know, many, because, you know, when you look up at the moon at night, you see dark and light regions. And, you know, we know that on Earth, the two main different kinds of regions that cover the surface of our planet are the land and the oceans. And um, so for a long time, you know, when the earliest telescopes were being built, people thought that the dark regions on the moon were oceans, and so that's why they still have names that often begin with Mare. So we have Mare Tranquillitatis, Mare Imbrium, and Mare is the Latin for sea. But then, you know, as telescopes started getting better, people started to realize that the dark regions of the moon were not oceans; they were rock. And after the Apollo astronauts in the 1960s and 1970s brought back the first rocks from the moon, um, people in labs all around the world looked at those rocks, and one of the things that really stood out was that those rocks were very, very dry. There was practically no water in those. And so for the next several decades, our view of the moon was that it was a very dry place. And in fact, it was that understanding that the moon was so much drier than Earth that led to, or that informed, some of the theories about how the moon formed. And I know you've talked about this before in some of your productions, and you know, one of our ideas for how the moon formed. The leading theory is that the moon formed in a giant impact. It was heated up and it lost most of its water. And so one of the pieces of information that led to the theory was the discovery that the rocks that the astronauts brought back were so dry. So we thought the moon was mostly dry, but there was this idea that had, you know, taken root sometime in the 1960s that, well, perhaps there could be places on the moon that were cold enough that if you somehow had water delivered to the moon, um, there might be some places near the North and South Poles where you have regions cold enough that that water could be preserved as ice. And so in the late 1990s, there was a NASA mission called Lunar Prospector, which, among other things, decided to test that idea by looking for hydrogen near the North and South poles. And one of the big discoveries from that mission was that, interestingly, there was hydrogen near the North and South poles of the moon, and that sort of lent further weight to this idea that, oh, maybe there's water there, because the water molecule is 2 parts hydrogen, 1 part oxygen, and we were seeing hydrogen, and we were seeing increased amounts of hydrogen towards the poles, where we knew temperatures were generally colder and where maybe ice could exist. And so 2009 was sort of the big discovery year for water on the moon. And so several things happened in 2009. So back on Earth, people were still looking at those rocks from the 1960s. Only the instruments that they had in the lab had gotten better and better and were now sensitive to tiny amounts of water. And so in 2009, scientists looking at the same rocks found that, there were very small quantities of water in them, much more than we had initially thought, even though, very still dry compared to the Earth. And at the same time, there were 3 spacecraft that visited the moon around that time. 2 of them were going to other places. So there was the Cassini spacecraft, which was on its way to Saturn. There was Deep Impact, which was going to visit a comet. And then there was Chandrayaan-1, which you mentioned. And all 3 of those spacecraft decided to look at the moon and see if they could find signs of water. Now, Cassini and Deep Impact were going to Saturn and to comets, to the outer solar system, where they were expecting to find water. And so the moon was sort of, a test of the instruments. They weren't really expecting to see anything. Chandrayaan-1 was going to the moon to stay in orbit. And it was interested in whether, maybe it could see some of this hydrogen near the poles. But what all 3 spacecraft saw right around the same time was that there seemed to be something resembling water, not only at the poles, but in fact all around the moon. What they saw was so we'd already seen the H part of H2O, and what Deep Impact, Cassini, and Chandrayaan saw was the OH part. And so here again, there was some uncertainty. Was the OH connected to another H? Maybe, maybe not. But they saw it all across the moon. And then there was L-Cross, which sort of dropped, and which followed a year later, and it dropped an empty fuel tank into one of the cold, dark craters near the south pole of the moon to see what came up. So kind of like, putting your foot into a puddle to try and look for water that splashes out. And in fact, that is what it saw. So it saw this cloud of ice and dust that was kicked up. And so that's how we discovered that there was water on the moon. But where the computer models come in is in answering some of the questions that we began to ask after that. So we now know that there is H2O in polar craters, and there seems to be H and OH in other forms all across the lunar surface. And so the questions we ask are things like, where did this come from? And how does it move across the surface? We seem to see it everywhere. Where does it come from? Where does it go? Is it still moving around today? And so those are some of the questions that I look at using computer models. So my PhD focused on the question of where the water came from. So one of the ideas, one of several ideas, is that maybe the water was delivered by a comet. So at various points during the moon's history, we have had icy objects from the outer solar system that have collided with the lunar surface. And during my PhD, I was looking at what happens to the water from those objects when they hit the moon. They're coming in at very high speeds. And so when they hit the surface, most of that water turns to water vapor. And then what happens to it? So I was using computer models to look at, where do the water molecules go? How many of them fly out into space? How many of them are destroyed by sunlight? And do any of them end up being trapped in those cold regions near the North and South poles? So we can look at origins using computer models. One of the things I do today is looking at the lunar exosphere, so the moon's very thin atmosphere. We refer to it as an exosphere. The moon has a very thin exosphere, even today, and there are various types of molecules that sort of still travel across the moon in various ways. And so some of the work I do today is trying to understand the behavior of the lunar exosphere. How do molecules move across the surface of the moon? What molecules end up being collected in the cold regions near the poles? There are some unexpected sources of, so if we think of water, there are many other molecules in the exosphere, and each one has its own story. But especially if we think of H2O, one particularly interesting source is visiting spacecraft. So whenever someone wants to land on the surface of the moon, in order to slow down when you're coming in from space, you have to burn some rocket fuel and fire your engines to slow down. And when you do that, one of the things that you release is H2O, this scientifically interesting molecule that's also released when you burn rocket fuel. And so some of the work I've been doing recently has been looking at unexpected sources of lunar water that we might bring with us when we travel to the moon.
This is so interesting. I mean, so basically, the more we go, the more water there will be. I mean, to a certain degree, in that
To
sense.
to to some extent, yeah.
Okay, so can I? So what do you think? I mean, I also know like solar wind can also produce water. There are other
Mm-hmm.
things as well. So two related questions, and you can connect them or you can separate those out. One is, in your opinion, and that's sort of like, I mean, I know scientists are very careful in terms of these things, but in your opinion, what is the likely source of most of the water on the moon? And second, perhaps the follow up to that would be, I mean, obviously, we are talking about being there and using this water. Do you think the water that exists is it's on the surface, or is it tied into the lunar or the moon's dust or regolith? Or is it sort of like, no, here it is, like, you can go in and here are some of those things. What do you think?
Yeah, those are really good questions. So in terms of the likely sources, so we talked about a few. We talked about comets and spacecraft, which are two different extremes. Some of the other sources could be, so you mentioned the solar wind, and we still think the solar wind might be a source of some of the water on the moon. And so the way that works is, so the solar wind is the stream of hydrogen and other charged particles that streams out from the sun and touches every object in the solar system. A lot of the solar wind is H, and so the idea for a long time has been that when you have the solar wind hydrogen encountering the oxygen in rocks on the lunar surface. So rocks are, there's silicon, oxygen, there's other stuff in them. But the idea is, you have sunlight meeting rock and creating H2O, creating water. It's kind of magical that you can have a rock sitting in the sunlight and and then you have water coming off it. So that's a potential source. Another source that's been of great interest and studied a lot recently is volcanic eruptions. So we know that the moon has seen periods where it was very volcanically active in the past. So when you look up at the moon today and we see those vast plains of dark rock, once upon a time that was molten rock, and there were active eruptions happening. And we know that when we have volcanic eruptions on Earth, volcanoes, they bring up molten rock, but they also bring up steam and a lot of gases that are trapped inside the Earth, and they release it into the atmosphere. And so there's been a growing recognition that something similar might have happened on the moon. That when you had these volcanic eruptions that took place over millions and billions of years, perhaps those eruptions brought some of the water and the things like carbon monoxide and other things to the surface and released it, and some of that material could also have made it to the poles. So in terms of what the most likely source is, I think it's very likely a combination of all of these sources, because we know that all of these things have happened on the moon. We know the solar wind still creates some water today. We know that there have been impacts in the past of comets and asteroids. And we know that there was volcanism, and at least some water was brought up to the lunar surface by volcanic eruptions. And so it's probably some combination of the three. And the big question is, well, what combination of the three? Did some contribute more than others? And I think there's some indication that the water that we see on the moon might be very old. And so there's sort of some thought of late that, perhaps the older sources, perhaps the volcanism or the comet impacts, played a more prominent role, because the solar wind delivers water to the moon constantly over time, but it also seems to be in very small amounts, and it's not clear whether water created somewhere on the moon where the sun shines can actually travel to the places where we see concentrations of water today. So there might be some of that going on, but it seems that the water on the moon might be very old. And the reason we think it's old is actually due to another recent discovery, an even more recent discovery, and that was of water ice near the poles of Mercury, which is the planet closest to the sun. It gets very hot, but like the moon, it also has very cold regions near the poles. Now, on Mercury, wherever the ground is cold enough, you see ice. There's a very good correlation between temperature and the presence of ice. But the moon is very different. On the moon, there are some cold regions which don't have ice. And there are some regions where it doesn't seem to be cold enough, but maybe you see a little bit of ice. And so the difference between those two objects seems like it might have something to do with the age of ice. And so there's some indication that Mercury looks the way it does because the ice is younger, and so the ice was deposited everywhere where it was cold, and there it stayed. But on the moon, what seems to have happened is that perhaps the ice was delivered a long time ago, and since then it's been broken up by some of it has evaporated, some of it has been hit by asteroids and comets and micrometeoroids and been broken up and dispersed. And so that patchy distribution seems to be related to age. And so it's possible that the older sources might have been might have delivered more of the water that we see on the moon today. But it is still a big open question. I think the other question of how easy it is to access some of this water. Generally, on all of the planets of the solar system, the older material tends to be deeper below the surface, and so if the ice we see at the moon is old, then at least some of it is likely to be beneath the surface. At the same time, we do see ice on the surface. So there are at least a few small patches of the moon where we do see a clear signature of something that looks like ice when we look at it from orbit. So there are some places where there does seem to be patchy ice at the surface. But if it is as old as it seems, some of that ice is likely to be buried beneath the surface. But I think, the real answer is we're not sure yet, because we have these observations from orbit. Um, but many of those observations were really made by tools that were not designed to look for ice. I mean, because so many of these questions have come up after we found the ice. And so the questions we were asking before we knew if there was any ice are very different than the questions we're asking now that we know there is ice. And so Chandrayaan 2 is orbiting the moon right now. It's trying to collect. It's only been at the moon for, I think, maybe a year or so. So it's still building up that data set. But Chandrayaan 2 is looking for signs of water. There's a Korean spacecraft called Danuri that is trying to take photos in parts of the moon that are very cold and typically very dark, but with a very sensitive camera. If you look at it at the shadows for long enough, you start to see some things. And so there's some stuff at the surface. There's probably more stuff beneath the surface, but there's still a lot that we don't know about the about how it's distributed, and is it, and also what else is present other than water, because if it was from volcanic eruptions, maybe there's carbon and sulfur compounds. If it's from asteroids, maybe there's ammonia and a different set of carbon compounds. And I think one of the measurements that will be very exciting to see over the next few decades is several countries have missions planned that will actually land near the lunar poles and really look for the ice up close. And so I think those will provide a lot of very useful information.
So this is so interesting. I mean, we think, or by we, I mean, in general, we sometimes think, oh, the moon. We know so much about it, but it's so interesting that this is the closest object. It's orbiting right here. We can actually see it, like right over there, and humans have been there, like to one part, like or some parts near the equatorial regions, and yet how much we don't know. And from basic questions in terms of, hey, I mean, some things that we can even detect, how much is it, where is it, I mean, we don't know. So that brings me uh to my final set of questions, and that is, of course, humans are planning on going back. And from what you are saying, I mean, it immediately, this question, how water got there, whether it's old or young or whatever, like those are all, if you can analyze it, you can actually say a lot about that. But there are competing interests, because people want to drink that water too, if they are there, or to use it for fuel or whatever purposes. How so what is your perspective on the coming human settlements on the moon, or the missions on the moon, which may compete? I mean, what you are saying, I mean, those are fascinating questions. And in that context, samples from the moon are precious for understanding the origins of the moon, for understanding origins of the solar system and things like that. But they may be competing with the need to use water for human presence. How do you see that aspect in terms of that?
Mm-hmm. Yeah, that's a good question, and it'll be really interesting to see how that story plays out in the next few decades. So, so the water is scientifically interesting. It's potentially commercially valuable. I think we don't really know quite enough to see whether it is sort of really commercially worth the money in terms of extracting it. Um, and I think this sort of so I so something I've been going around telling people, um even if they don't ask, because I thought of it as, so planetary science is kind of, has always been about sort of three questions. There's where are we, and how did we get here, and where do we go next? And I think the moon is, recently bringing to the forefront a fourth question, which is, how do we interact with the environments of other worlds that we visit? It's something, that we think a lot about on Earth. I mean, the impact of human activities of all kinds on Earth has sort of been very has been increasingly visible as the years have passed. And I think that's a question that we are going to have to start answering on other solar system worlds as well. It's a very scientifically interesting question, and we have an experience from Earth that we can build on. But I think it, I think it's so several thoughts. So I think one thing that's important is to really understand the environment before we start changing it in extensive and potentially irreversible ways. I think that would be a good thing to do. But I think the other thing to realize is that it's almost inevitable that whenever we go somewhere, we will change the environment in some way. Even the process of trying to understand the environment involves changing the environment in some way. And so, so in some sense, some degree of environmental change or contamination is inevitable. But what we can do is to try and understand and to try and measure those changes. So to sort of keep our eyes open and think things through as we are proceeding. And so, I think that is sort of how, we as humans can best approach that problem, to recognize that, some degree of change is maybe inevitable, but to try and measure that change, understand that change as much as possible, and use that understanding to shape our decisions. And those decisions could take different forms. So, for instance, we talked earlier about how we started to discover new things from the same rocks just because scientific techniques had advanced so much. The same thing might happen in some of these permanently shadowed regions. Maybe there are science questions that people will ask many decades from now that we haven't even thought of yet, and they'll have ways of answering those questions that we haven't thought of yet. So, so some of the things we might end up doing, perhaps we decide that we're going to try not to go to some parts of the moon to sort of minimize the environmental changes in those regions and preserve them for future generations to explore. Or perhaps we might find that the environmental change we cause is kind of minimal, and maybe and maybe we make different decisions. But but I think it's sort of knowing what we're going into is I think really important.
Okay, so I want to ask one other question regarding that. You are a co-author on a paper that actually recently came out,
I've
and
never seen it printed out before. That's wonderful.
I'm a little old-fashioned, sort of like, I do like to print out. But so the paper is called "A Call for Indigenous Partnership in the Return to the Moon," and there are a bunch of authors on it, and you are one of them. Uh, I mean, I think it's really important to some of the conversation we are just having. So, can you tell us a little bit about what this paper is and what it is calling? What is the partnership?
Mm-hmm. Yeah, of course. So I started thinking about indigenous perspectives on the moon a few years ago when, so this was around 2016, 2017. There was a lot of talk about um, going back to the moon. And there was a lot of talk about resource extraction and colonization. And I mean, I'm from India, you're from Pakistan, and so colonization brings up a whole lot of things. And so I was like, wait a minute, let's not colonize everything. And but colonize anything if we can help it. And and then I think sort of hearing that come up in conversation in my sort of scientific space sort of made me take a step back and think about, hey, what is it that we're really doing here, and who is making decisions and why. And I live in the United States. I've lived here since 2010, and so and so this has kind of become my country, as much as India. And I think, of course, the United States is sort of a place where the colonizers never left. Um, and but at the same time, um, the indigenous communities have been incredibly resilient, and are still vibrant, and still survive and thrive today. And I was talking once to a colleague about how uncomfortable thinking of space exploration as colonization made me, and because people often compare voyaging into space to the journeys of Columbus and the other Europeans, which is sort of a tremendously problematic analogy. And so the colleague I was speaking to said, well, I always think of the real analog, or the real analogy for space exploration as being sort of the early voyages of Polynesians and other indigenous communities, when they sort of set sail across the Pacific Ocean with only the night sky, and some common sense and some indigenous science to guide their way. And they undertook, tremendous voyages, and they went to places, and not to conquer them, but to sort of live with the land, and um, so I went on this whole journey, and I think one of the things I came to sort of realize, was, and of course many people had realized this before me, and had written about it, but I think when we think about this question of how do we interact with places that we visit, and how do we learn to live with the places that we visit in a truly sustainable way. I think there is a lot to be learned from the perspectives of indigenous communities around the world. And of course, not all indigenous communities are the same, but one thing that they have in common is that they have longer relationships to the places they live in than any other communities. And so they are the experts in terms of understanding how to observe and how to understand a changing environment, and adapt to it and take care of it in a way that it continues to sustain and support the lives of the people who live there. And those are the kind of things that people often think of when they're in sort of very futuristic visions for space exploration. I mean, when you think of living on another planet, I mean, if we can't live on this one, and we don't seem to be doing a particularly good job collectively of living on this planet, how can we ever hope to live on another planet? And maybe the sort of one part of our human family that has some answers to that are the people who have lived in certain places for thousands of years. So I think there's a lot of wisdom there that I think is kind of dismissed in in space exploration in particular. I think also in general the relationship between science and colonialism is fraught, and there's been a lot of extensive writing and thought on that. But I think in space exploration in particular, indigenous perspectives, sort of broadly speaking, have a really important place that's not often recognized. And so the article that we wrote, so it's something that I co-wrote with colleagues who have backgrounds in sort of in literature and science and public policy and many different fields. Some of those colleagues are from various indigenous communities in the United States. But it's something we wrote to kind of call attention to the importance that the perspectives of indigenous communities have when it comes to developing sensible space exploration policy. So one of the things that we call on in that article is for NASA, which is the National Space Exploration Agency
Right.
in this country, to start consulting and collaborating more meaningfully with indigenous communities in the US, because it's NASA, but I think it's something that the world as a whole would really benefit from doing.
This is such a fantastic thing, and I'm glad that you contextualized it, that about the way we think about nature, right? And that's the use of the words too. I mean, oftentimes it comes in that you conquer nature, like, or sort of like, you sort of like, subjugate nature and so on and so forth, rather than living with nature. And I really appreciated your point about the fact that a lot of these, especially a lot of the indigenous groups, and with all the diversity that comes with it, that oftentimes they have a relationship with the land that they are in. And of course there are variations to it, but it's more than oftentimes what is driven through, in particular, through capitalism. For
Mm-hmm.
example, I just had a chance last week, in fact, to go to, I was visiting New Mexico and went to Bandelier National Park, where you have these wonderful dwellings which are basically in the mountains. And it's just like, it's part of nature. People are living there. And in fact, one of the things that occurred to me at that, when I was visiting those, was something like even living on the moon or Mars. I mean, if you're thinking about lava tubes or other types of things, and it was like, well, it would be something that's a really good lesson to learn from it. So I really appreciate, for people who are interested in this paper, I will put a link down in the description of this video so people can actually look at that. One last question, and that is, any particular science fiction films that you are interested in, or books, like, that you go like, what, I read this is fantastic, or this is something that inspired me, or this is something that I looked at it, read it, or watched it, and I was like, oh, that's something is connected to my work, or something like that. So give me an example.
Yeah. So, big Star Trek fan. I like so many things about Star Trek. I think it offers a very optimistic view
Yeah.
of what the future might look like. And I've always said I'm not leaving this planet until we have decent starships, and whatever political system is in place in the Star Trek universe. But I think another sort of body of work that I found very interesting is Kim Stanley Robinson's Mars books. So there's Red Mars, uh, Green Mars, and Blue Mars, and it's about it takes place over many generations, and it's about humans going to Mars and living there. And it's uh, some parts of the book are fantastic. Some parts are very long and very boring, um, and I don't always agree with with all of the perspectives. But I think it's what struck me about those three books is just like how remarkably realistic they are in kind of thinking through the problems that, or not necessarily problems, but the debates that we might have
Yeah.
in the process of living on another planet, and how those debates might work out. I found that really interesting. So especially the first book, Red Mars, sort of centers on a debate between those who want to change Mars to become more hospitable to human life, and those who want to keep Mars what it is. And I just found those debates sort of just really fascinating. And I, I and I think if I had been in that world, I would probably, I think, have been on the side of those who wanted to keep Mars the way it is. But that isn't the side that ends up prevailing in the novels, and I still found it really interesting just what happened afterwards. And it's I thought that was a really good story.
And I should mention that Kim Stanley Robinson, I mean, he is still deeply invested in thinking about the Earth as well. And more lately, he has been writing about climate change. He has been writing about what we are doing to this planet as well. And so he's one of
Right.
those more thoughtful guys who is really trying to grapple with. But I agree. I mean, his I haven't read the last one, which
It's
is
the
about
Ministry
the.
of the Future.
That's right. Yeah. Did
I
you? Did you? Did you?
I read that as well, and I thought that was very interesting as well. It's
Okay, because I got a little scared about the because I knew that there is not much narrative in there. It's more about sort of like the governance aspects and how to think about
yeah,
these.
I think the really interesting thing about Kim Stanley Robinson is that, I mean, sometimes when people talk about realistic science fiction,
Right.
they're, oh, did you assume the right temperature of Mars? But I think and which I'm like, whatever. Does it really matter? But I think Kim Stanley Robinson's realism is sort of in the realism that with which he writes the relationships between the human characters. I think that is really spot on, and that's hard visioning to do, and he does it well. And his writing is sometimes a little bit hard to read, but it's but he writes well.
That is so wonderful. So there are a lot of recommendations as well. Well, Dr. Prem, thank you so much for your time, for a generous time. It was a lovely conversation. I really had a great time, and I hope people learn a lot from the importance of the moon, just from a science perspective, from water on the moon, which may be necessary if when we go there, and when we go there, what kind of things to think about. So all of those things are embedded in there. So thank you so much.
Thank you so much for having me, and thank you for listening.